Okay, so let's begin.
Okay. Thanks for Anish
No,
for
can you?
inviting me.
Sorry, can you share the screen? Your
Yeah,
screen is
yeah, sure. I'm sharing
just
now.
yeah, just a moment.
Okay. Can you see it?
Yes.
Yes.
So
I think
welcome everybody to this week's Majorana-Raychaudhuri seminar series. We are very happy to have Chen from Schola Normale Superiore, Pisa, and he's going to talk about strongly coupled sectors in inflation, gapless theories, and unparticles. I will send you a reminder when 5 minutes are left.
okay.
Yeah.
Yeah, thanks Anish for inviting me to this seminar series, and I'm very happy to uh, show you my work on archive in March. So recent works about the strongly coupled sectors in inflation. So let's start. Um, so my seminar will based on uh, let's say 4 works and 2 already be on archive. One has the same name with my seminar, and the other one is called the Bananas are Particles. So it's a special case where I was studying this surrounding couple sector inflation. I will mention this during this talk. And yeah, and then in this work, we focus on more on this differential equations and cosmological bootstrap part. And if time permits, at the end, I will tell you something. Well, first one in preparation is this dark water stories, the model building part of the strongly coupled sectors. And also something on the research is for the Gapless series and the relation to holography. Okay, so first, let me briefly mention this cosmological collider physics. So we know that during inflation, um, because the energy scale is pretty high, then in principle we can generate heavier particles than the usual particle experiments like HC could approach. And then they will leave signals in the late time, well, in some sense, relics like in CMB, like in this um, curvature perturbations. So the previous studies on this curvature perturbation, also people call it non-Gaussianity, which means the part that deviates from the usual Gaussian model. So Gaussian model are free models, like the models of free series. And well, non-Gaussianity is also called the cosmological correlator. And in this sense, most works are focused on the weakly coupled scenarios, which means people consider a free theory and perturbations, like couplings to the inflatons. But it is very less explored for strongly coupled scenario. But this strongly coupled doesn't mean like we're considering a sector that strongly couples to inflaton. No, it's still weakly coupled to inflaton, but strongly coupled in itself. So it's more like the composite Higgs story, or like the QCD making like hydrogens, pions. But in this case, how should we start? We can classify the strongly coupled case mainly in 3 scenarios. So first is when the mass gap is the energy needed for exciting the lowest state in the energy spectrum. The mass gap is very much smaller than the Hubble inflation. So this is the Hubble constant during inflation for sure. Well, approximately they are conformal fields because they have a continuous spectrum. For these kind of scenarios, people call this unparticle. Like for Georgia, I came up with this in 2007. Some Rondo-Sondrum second model, or this hidden valley scenarios. And also we can consider the gapped cases. Like I mentioned previously, if the mass gap is comparable to Hubble or much larger compared to Hubble, then, well, the second case is most interesting, right? Because if it's very much very much larger compared to Hubble, then in principle, this is some very heavy single particle, single massive particle state. But we expect some new feature to happen when the mass gap is compared to the Hubble constant, and this is what I will emphasize in next work. In this work, we will focus on this approximately conformal field scenario, which I will call them unparticles. And this is also interesting because in this case, the model actually comes to a scale invariant phase. So they're not really in this QCD-like case where you got the bound states and then you still got like real composite particles. In this sense, it's not composites like pions and hydrons. It's a CFT, and I will tell you a bit on the basic properties needed for understanding this work. So first, let me introduce this language of EFT of inflation first, because this is part of the key ideas on our strategy how to compute these cosmological correlators. In this EFT of inflation, it means we absorb the inflaton into the, let's say, using this unitary gauge, we regard the inflatons as the goldstones when we break the time translation symmetry. So in this sense, if we take the decoupling limit, which means, okay, the gravity is not active, it's a fixed curved background, then we get the scalar perturbations as this pi. Well, it's called pi because it's also kind of a pion. We should notice that this pi always come in derivatives. So they're always derivatively coupled, and this is very important for the next step where I introduce our strategy. So first, let me say, if we couple this scalar operators, it's the operators when our series are already in this conformal phase, then they are scalar operators labeled by the so-called scaling dimension, and we denote it with delta. So at the leading order in derivatives until this linear order in O delta, then we can write out the mixing Lagrangian like this. This is a coupling constant. This is a scale for EFT of inflation, and this is the like G not +1. So it comes like this. And during our computation, we will use this effective action, which we consider the coupling to conformally coupled scalars first, because the mode function of conformally coupled scalars are much easier to manipulate than the usual inflatons, as we will see, I think, in the next slide. But using this weight shifting idea, then we can match the correlation function computed from conformally coupled scalars to derivatively coupled inflatons. So first, we use the flat slicing of the theta as usual in inflationary cosmology. And we can see the mode functions for conformally coupled scalars is pretty simple, right? It's the scaling and some plane wave, just like in flat space. And this is the mode function for inflatons, and at least it has two terms. And this is the 2-point function for scalar primary operators in CFT. This is completely fixed by conformal symmetry because it's a very strict constraint. So for at the 2-point function level, we can directly, well, let's say bootstrap the 2-point function. Okay, so let's consider this gap much less than Hubble case with unparticle exchange, which we fully solved. So first, the integrals to solve is like, well, for S channel, the 4-point function, we have 4 sectors, right? It's like this in-formalism construction. And this is the strategy. So we compute the conformally coupled scalars correlation function first, and then we perform this weight shifting process, which means people already found in Bootstrap, in this cosmological Bootstrap papers, uh, a special differential operator that if you act on the correlation function of 4-point correlation function of conformally coupled scalars, you can match them to derivatively coupled massless inflaton correlation functions. I will show you later. So this is our strategy. And then, okay, that's the hard part. There are some integrals to solve, right? Like 4 sectors, and these 2 sectors are the complex conjugate of these 2 sectors, so at least we have 2 to solve. So for this first one, which I denoted as I++, we can see it's a triple integration over some rational functions with twisted parameter. Because delta is the 4-dimension scaling dimension. Because well, people should not get confused with this delta also in cosmological Bootstrap papers, where the delta is actually the 3-dimensional scaling dimension, the boundary, like the scaling dimension near the boundary. But in our case, because we are considering some conformal field in the theta, so it's the 4-dimensional scaling dimension, and we take it to be a general real number. Okay, and this is the plus minus sector. It's a bit simpler, but still it's a triple integration. I will not go into too much into the details of the computation because it's pretty complicated, but I will scratch this basic procedure. So first, for this direct integration, finally I choose to use the Mellin-Barnes integration because the Mellin-Barnes is somehow the plane wave expansion in hyperbolic space. So it will actually simplify the computation, even it seems to be scary in the first place. And there are 2 important formulas. This one that can help us to perform the real integration, and this one is like so they are combined. Like we need to transform the real integrals into this complex counter integrals first, and then try to integrating over this. Let me just directly show you the result. And you don't really need to like really look into it because later I will show you plots. It's just to see this is a very complicated case where we have a symmetric, like it's written in the symmetric form of 5 Appel F1 function. And Appel F1 function is defined like this. So it looks like a product of 2 hypergeometric function 2F1, but with mixed parameter. As we can see here, they mix this alpha and gamma. So it's not the product of 2F1, 2 hypergeometric functions 2F1. Okay, we look back here again. So we can notice that because in our expressions, it seems like if we have a integer delta, then the coefficients will become these coefficients will become integers, right? But from this expression, we can already expecting some divergences if we have negative values or negative values, because here it's like the delta -1 and 2 minus delta, but also delta equals 1 is already causing some divergences. So by looking at it, we can expect some divergence for all integer deltas. And this is what I and my colleague Tom emphasized in this paper, Bananas and Particles. We showed that these divergences for integer delta actually corresponds to the banana loops for conformally coupled scalars. So these divergences are natural because they are the divergences in loops. Okay, and well, this is the first bootstrap example in loops because we already know that the loops in cosmology is already well, very hard. Okay, let's get back to these inflationary correlators. So recall that regardless of the prefactor, then this is the mode function of massless scalars. This is the mode function of conformally coupled scalars. And the wave shifting operator is a differential operator, looks like this, that can relate this curly phi k1, k2 to this derivatively coupled phi k1, k2. And U, sorry, did I mention this definition for U and V? Yes. So it's a bit like the, well, let me not mention it. So here, for simplicity, we define this capital X1 and capital X2 to be the ratio between the external momentum over the exchange momentum. The 1, 2, and 3, 4 are the label for the external particles, right? And the U and V are just the inverse. So this is a K over K1, 2, V is a K over K3, 4, and K1, 2 is K1 plus K2. So the total momentum. And well, in some cosmological bootstrap literatures, they will use the total energy because it's an analog to the total energy in the amplitude literatures. Okay. Yes. Now we can relate the dimensionless part, which is written in terms of UV for conformally coupled scalars to inflatons. And this S is the usual Mandelstam S. So for quasi de Sitter, now we have this inflationary trispectrum. But to the leading order, the inflationary trispectrum will not fill the slow roll parameter, the usual epsilon, if we consider single field slow roll scenario. So first, when delta is smaller than 3 halves, this trispectrum scales for small s as s to power 2 delta minus 3. So for small s means in the collapse limit. It's also called the collapse limit. Because in momentum space, the boundary 4-point function has momentum conservation, right? So it's a closed geometry, and the collapse limit means 2 vertices collapse into each other. And when the delta is larger than 3 halves, it's not like smaller than 2, because in principle we can perform an analytic continuation to all larger delta. This is the property for a Bell F1 function. Then the inflationary trispectrum scales for small s as s0 to power 0 is a constant. So, well, this degenerates with the property of contact interaction, the equilateral shape. And also for this S2 fractional power, it degenerates with the light mass scalars. Because experimentally, we just measure the power on the S, right? So if we just got some fractional power number, you cannot distinguish between the free light mass scalars or unparticles. So like I showed here, the left panel is the massive scalar exchange for mu equals 3, and which means this is already so-called heavy scalar. And this is the unparticle exchange for 7 halves. It's like the free massive scalar will have this damping oscillation, but for unparticles it's just a bit flat. Well, not a bit flat, it is flat. Well, we can also get the bispectrum, but not from a naive way to take the soft limit of one of the lengths, because then it would just result in 0. But if we take a mild breaking of the theta isometries, which means now we involve this one higher order expansion, then we can generate the inflationary bispectrum like this. So this is the relation between derivatively coupled inflaton and the conforming coupled scales. This way we can define the bispectrum. This is a 3-point function. Okay, now let me show you the result. It's similar to the trispectrum. So when delta is smaller than 3/2, it's like degenerates with light massive scalars. And if it's larger than 3/2, it degenerates with an equilateral shape, like the delta phi to the fourth, and then you take one leg to the contact interaction of delta phi to the fourth, and then you take one of the phi to the one of the k to the soft limit, like what Paolo Criminelli was doing. This is the summation of a position of peaks, and I will show you later in the following the plots. This is how we define the shape function relating to the 3-point functions. Okay, so now here we can see if we take it to be the isosceles shape of the triangle, 2 edges to be 1, and we plot with respect to K3, we can see they all peak in the equilateral shape. So it's just the detail shapes are different, but naively it degenerates with this delta phi to the 4 contact interaction. And also, if we have, so sorry, this is for delta smaller than 2, and also for delta smaller than half integers. Like, yeah, let me emphasize on this. So for delta between, because delta has to be larger than 1, there's some unitarity bound. Between 1 and 2, it's just looks like a equilateral shape. But for the delta larger than 2, but smaller than half integers, they will always look equilateral like this. It's like the 2.2, 3.2. And this is a novel new shape for half integer and around the half integers. I will show you later. And for this between the half integer and the n+1, here I called it negatively equilateral. It means, well, you can also say it degenerates with the orthogonal shape. So it's negatively peaked around the equilateral and then got this kind of shape. But this is the new shape we can see from half integers. But you cannot see it from 3/2. It starts from like 5/2, 7/2. It's like it's oscillating, but not only oscillate near the squeeze limit, but it oscillates throughout the full shape. So we can regard this shape as something in between this equilateral-like shape or the orthogonal-like shape. Right? It's like this, the negative extreme needs to be larger, and then this maximum extreme needs to be smaller. And for half integers, they become saddles, like flat near K3 = 1. It's a equilateral triangle shape. And well, this is the phenomenologically interesting part. Well, anyone has questions till this point? Because then I will tell you something
I
after
don't
that.
see any question in the audience.
Okay.
Maybe we continue.
Okay. Thank you. Um, so here I just briefly scratch how we can study the other scenarios. So because it's a CFT, so in principle, if we want to grab some ideas, we can take the ADS CFT correspondence and try to study it within the ADS dual. So for large gap, it actually looks like there's an end word brain cutting up the geometry inside the ADS bulk, and then it becomes a bubble of nothing. If we take the DS slicing of ADS, then we just use some WKB approximation, and we will see it's a free massive mode with a exponential suppression in the prefactor, which means it is very suppressed. Well, but that's what we expect for a large mass gap, right? Because you cannot really, in the limit, you cannot really excite even the lightest state. So it's exponentially decay. And yes. And for model building part, maybe some of you have interesting. I call it a dark walker because I realized there's some walking dynamics. So the idea is I try to find a simple model to give both this primordial non-Gaussianity as I introduced to you before, and also the radical abundance for dark matter, because these particles have to be something after inflation, right? They will not just vanish. So I look into this the gauge series because it is well known that with a certain range of fermions, then the gauge series will flow to the IR fixed point, some non-trivial IR fixed point, which is CFT. So this is a kind of a property of a conformal series. The IR of RG flow is just three possibilities. So one is theory becomes gapped, just like the usual QCD, or the theory becomes like some theory only with a massless mode, or it becomes a scale invariancy. So uh, this range of number for the, flavors of fermions is called the conformal window. And this is a beta function for gauge coupling in the usual conformal window. So this is the Gaussian fixed point. And now we turn on the gauge coupling G and we see this is negative, so it becomes stronger and goes to some IR fixed point. And people, well, argued, or you can prove that there also exists some UV fixed point. But as you can see, in this regime is positive, which means this is a stable IR fixed point. And we don't expect this gapless particles to be dark matter, because we know dark matter is a particle-like. It's not radiation-like. But the particles, if you think about it, it's a field with a gapless spectrum, which means some portion of it is around the, well, you can regard it as some effective zero mass or light mass part, right? So it behaves more radiation-like. And in this sense, the unparticles has to be something after inflation. It has to be gapped. It needs to get some bounce states. But as we can see here, this is a stable IR fixed point. So even like here, I showed you. Sorry for this. with this linear mixing, if the delta is between 1 and 2, okay, now this is 2 plus something smaller than 2, and so this is a relevant operator, but it cannot be large because if it's large, then it will break up the structure of inflation. So it's a small relevant uh, perturbation. But then, since the beta function looks like this, you cannot really drag it away from the fixed point. But then this year, there's some very interesting work by uh, Anna Heisenfreiser and her collaborators. There's some special gauge series. For example, SU2 with 4 flavors or SU3 with 8 flavors, that their beta function has merged the fixed point. And this is very ideal for my case because even for a small relevant deformation, I can expect some working dynamics, right? The theory will stay near this fixed point for very long, but as long as the energy scale keeps going down, finally it becomes some bounded states. So this is this linear mixing induced working dynamics. It sounds very nice, and this model, I'm writing a new work on this model. I think I expect it to be out in 1 or 2 weeks. So if some of you are interested in thinking in a specific model way, then this is a story I would like to tell you. Okay, so there are some future directions I would like to mention. So first is the shapes in gapless scenarios for sure, because initially unparticles are uh, filled with large anomalous dimension and become scale invariant. But later people extended this definition into, well, unparticles can still acquire mass as long as it has a large anomalous dimension. So uh, we can study the shapes in gapped scenarios for these gapped unparticles. And also, since during this discussion, actually the background we really looked into our pure de Sitter, and then the quasi de Sitter, which means we mildly break the well, let's say the boosted symmetry. But for more practical case, we can look into some booster scenarios, and there's some recent works by Donggang Wang and Guillermo Pimentel on this kind of direction. The third one is some observational data analysis, some real data analysis from the current satellite data for bispectrum and trispectrum. And since, as I emphasize here, to distinguish between, let's say here, okay, to distinguish between light massive scalar exchange and this small scaling dimension on particles, we need the analysis of full shape. Like here, like this, right? We need the analysis. So it is some hint that even previously people claimed that the squeeze limit is kind of a particle detector, but it's not a precise particle detector. There's some degeneracy between different kind of fields and requires our knowledge for analyzing the full shape. Okay, so there's a rich landscape to explore, and this will be the end of this talk today.
Thank you for the nice talk. We have now time for question answer. Anybody in the audience want to ask any question?